This is number 9 that I cooked up. I'm in love with. This is just a great question. A twice differentiable function. That means that it has at least 2 derivatives. So that's actually good news. It's not weird. There's not corners or cusps or vertical asymptotes. And it's defined by that f of x. Notice that a, b, and c are all constants. So we don't know what they are, and we have to figure out what they are. There's a local max at the point 114, and there's a point of inflection at -3 comma something. Find a, b, and c. Okay. At first, it doesn't seem like there's a lot to go with, but I think we might be surprised here. Let's go ahead and start out by taking the derivative. Remember, a is a number, so 2 times a is 2a. So plus 2a x to the first. The derivative of bx would be b. Just like the derivative of 6x would be 6. It's, b is just a number. And the derivative of c is 0 because it's a constant. All right, so that's the first derivative. And let's get a second derivative right next to it. I'm drawn to this point of inflection part. There's a point of inflection at x equals -3. Points of inflection happen when the derivative is either undefined, which of course this is defined, it says twice differentiable, or points of inflection occur when the second derivative is 0. That has to be the case. But it says that the point of inflection happens when x is -3, so they're giving me the x as well, which means I can figure out what a is. I've got 2a. I'm going to kick this to the other side by adding 18. 2a is 18. A is 9. All right, so that's one of them. 1 down, 2 to go. Because a is 9, I can use that in other equations. I can come over here and be like, oh, a is 9. This is going to be 18. That's 18x. So that will help. Next, I see that 1 comma 14 is a local maximum. Right there. So that means that if x is 1, then the derivative would have to be 0, because when you have maxes or mins, slope is flat. That's how you find it. You set the derivative equal to 0. That's 3 plus 18. That's 21 plus b is 0. So clearly b has to be -21. So I've got a and b. We're going for c. Okay, I needed a little bit of space, so I cleared some things out. Here's the one thing I haven't really used, other than to get the derivatives with it. But if 1 comma 14 is a local max, 1 comma 14 also has to be on the curve itself. So think about 114. 1 is the x, 14 is the y. Let's try this out. Let's bring this down. Y equals, so 14 equals. Remember, x is 1, so we have 1 to the third, that's 1. Plus a x squared. Well, a is 9, though. Here, I'll make it official here. 1 to the third. Plus bx, but b is -21. Plus c. So now we can figure out what c is. Let's go ahead and go to work here. 14 equals 1 plus 9. That's 10 minus 21. That's -11 plus c. We add 11 to both sides, and c is going to come out to be 25. And those are your 3 answers: 9, -21, and 25. That's a great problem because you can't use a calculator. You have to know how to take derivatives. You have to realize what local maxes and mins and what points of inflection entail. And then it's just a bit of rudimentary algebra 1. So good stuff in that one. Easy to grade too, which I like as a teacher, I won't lie. All right, number 10. It says let g be a differentiable function. The word differentiable just simply means you're able to take derivatives everywhere. Okay, so no funny stuff. That's a good word to see. G is a differentiable function with only one critical number. X is -6. Interesting. All right, so there's only going to be one max or min. It'll happen at x equals -6. I feel like I need to make a picture of this just to see what's going on. So let's just investigate. Again, just a sketch. Here's -6. So somewhere along this dotted line is where the action happens. And it says that G goes through the point -6, -7. All right, so I'll just mark that. There's -6, -7. So it's going through there. All right, let's see what's going on here. Here's -8. Here's -4, obviously not drawn to scale. It says that the derivative at -4 is negative, which means if I'm along this dotted line here, my slope or derivative is negative. Okay. And if I'm along this dotted line, it says that the derivative, g prime, or slope, is +3, so it's just rising. But there's only one critical number, and the critical number is that, or the critical point, I should say, is the -6, -7, which means that the -6, -7 has to be an absolute max. So that -7 is the maximum value. Here's how I know. This drawing, this has to be a little bit lower so that it comes along like that, and that's the max. Now some people are like, well, why can't it, do this and go up higher? Well, then you'd have more than one critical number. And it says there's only one critical number, and it happened at -6. So because of that, you have to have a max. Number 11, based on the graph of f of x, find the sign, either positive, negative, or 0 for each value. These are kind of cool as well. Let's start with the first grouping of 3. I'll take myself to when x is -1, which would be right along this line here. You can see I'm right here at this point. Well, obviously at that point, I'm above the x-axis, so f of -1 is positive. In fact, just for the record, it's +4, but I don't need to say that. F prime of -1 is 0 because it's a max. And f double prime of -1 is negative because I'm concave down like a frown. So that's kind of cool. All right, let's move over to +1 this time. F of 1 is positive. You're above the x-axis. Looks like it's 2. F prime of 1, the graph is falling with a negative slope, so that's negative. And f double prime of 1, I tried to make it look like a point of inflection. That's what I was going for, so we're going to call it 0. All right. And finally, last but not least, let's take ourselves to x equals 4. Right here at f of 4, obviously that's negative. You're below the x-axis at a height of -2. F prime is 0 because it's a minimum. And that portion of the graph is concave up, so f double prime is positive. There you go. Easy to do, easy to grade for a teacher, but yet a lot of knowledge is shown. You're not going to go 9 for 9 just out of luck. You have to know what you're doing. So that's cool. Okay, I've given you a graph of f of x. You have to graph both the derivative and the second derivative. So I'm going to make the derivative green, the first derivative I should say, and then the second derivative I'll come back and I'll make that blue. Now because there's no equation given to you, this is simply a sketch. You don't have to be perfect, but you do have to be reasonably good, reasonably close. So I'll show you what I mean by how reasonable you need to be. Let's start with the first derivative. The first thing I do is I look for where the maxes and mins are. Because at those places, the first derivative is 0. So when I go to graph the first derivative, I better be on the x-axis at 0. So I'm going to put dots there. All right, cool. Now I'm going to get rid of these slopes. Those are just training wheels for me. The green dots stay. right about here at -1, just looking at that, it looks like the slope is probably right about 2, up 2 over 1. And so I'm going to put a dot right here at 2. Again, this is just a sketch. I'm doing my best. I can see that over here, the slope is very negative. Over here, the slope is very negative. So the graph's going to be sort of like an upside down parabola of sorts. And you can see that, like here, to me, it looks like you're going, down 3 or 4 and over 1. Maybe it's not quite as steep as I made it. Maybe I want to go more like this. It's going to be kind of parabolic. So anyways, it's a sketch. All right, so that's the first derivative. Let me get rid of some of these extra markings. Now for the second derivative. Again, I look for the maxes and mins. If the slope is 0 there, that's the slope of the first derivative. That's the second derivative. So that's going to be 0. All right, cool. Let me get rid of that line. Interestingly enough, did you notice how the second derivative 0 lines up with the original graph being a point of inflection, which is perfect. That looks great. Right here, it looks like the slope is -1. Here, it looks like the slope's more like maybe -2 or so. If I was to go right about maybe here, looks like the slope might be +1 or +2. So, I'll put +2. You can see that a line is forming. And it's not perfect, but it's close. It's a sketch. That's the second derivative. One more thing to point out. The original graph in red was a cubic function, third power. It makes sense that when you take derivatives, you would go down by a power, as we know from chapter 2. So that means that when you take the first derivative in green, it should be something squared, and it does look like a parabola. When you take another derivative, you're down to first power, which is a line. So yeah, I totally agree. This looks great. These graphs make sense. We will practice this quite a bit. This is a skill that you want to be good at. It's going to be heavily tested. Number 13, sketch a continuous curve, so no asymptotes, no discontinuity anywhere, having the given properties. Well, let's start with the easy stuff first. It says that f of -1 is 2, so that's the point -1, 2. It'll be here. But you're also going through the point 7, 2. 1, 2, 3, 4, 5, 6, 7, 2. All right, so it has to hit those points. Now I have to translate. First derivative positive. You know what that means? It means the graph is rising. It's increasing. So the graph is increasing if x is greater than 3. Let's put a little dotted line here. This is not an asymptote. This is just me helping myself. So if I'm to the right of that dotted line, I'm rising. If I am less than 3, to the left of the dotted line, then the first derivative is negative. I'm falling. So basically, I have to go through this point, falling. Once I hit that, I have to start rising again, which means that the minimum is somewhere along the line, x equals 3. It doesn't necessarily have to be at, -1/2 or wherever I happen to be. As long as you go through these 2 points, -1, 2, and 7, 2, it doesn't matter how fat or skinny your parabola is. It's good either way. And finally, it says the second derivative has to be positive all the time, which means you have to be concave up, which my graph already is concave up, so I'm good to go. So really, this just described a parabola whose vertex is on the line x equals 3 somewhere, and it's opening upward, hitting those 2 points, -1, 2, and 7, 2. Some people are like, well, could it be an absolute value bouncing off of the dotted line? Couldn't it just come through like this, and then bounce and come through like this? And the answer is no, because the second derivative has to be greater than 0. It has to be positive. if you use absolute value, your second derivative equals 0. And that's not what the directions say. So I need to get rid of that. And there's my correct answer. All right, this is the last one, and man, we're going out with a bang, it looks like. Again, sketch a continuous curve having all these properties. Let's start with the easy part first. Again, you're going to go through the point -3, 8. 0, 4. And 3, -1. Okay, so far so good. Next up, it says that the slope at -3 and the slope at +3 are both 0. So those are critical points, or critical numbers. So I would expect that right along this dotted line and along this dotted line at 3 and -3, you're going to have maxes and mins. It looks like that first one in quadrant 2 is going to be the max, and obviously the one in quadrant 4 will be the min. Let's see what else it says. It says that the first derivative is positive. In other words, the graph rises if the absolute value is greater than 3 of x. That means that if you are out towards the edges, if you're out here and you're out here at like 4, 5, 6, 7, or -4, -5, -6, you're going to rise. And that would make sense if this was a min and I was rising. And I was rising to get to this max. I would be rising out, on the outskirts. And then it says that the first derivative is less than 0, negative. That means the graph is decreasing or falling if the absolute value of x is less than 3, meaning between -3 and 3. And sure enough, that kind of jives with what I'm seeing, because the graph would have to fall, because this means falling right here. And then finally, last but not least, your second derivative. Second derivative less than 0 means concave down, like a frown. If you're less than 0, and that looks concave down. The second derivative greater than 0 is concave up. If you're greater than 0, and that looks concave up. So there you go. That's my answer. The only things that I have to have are I have to go through these 3 points, of course. This has to be your max, your local max. This has to be a local min. The 0, 4 is a point of inflection. And you're good to go. All right, that's a big section. Hopefully that made sense to you. Take care.